with that, I can start with lecture 3. I posted the note-taking version half an hour ago, so I'm sorry for not updating last night because I had to do like last-minute edits. So what I'm going to do today is I'm gonna continue explaining the Hooke's law, and now it's generalized. So it's just like a continue of the work that we did before. So if you remember, we have a Hooke's law, which is stress is equal to modulus of elasticity times strain. And you solved in the in-class assignment a couple days ago, like a very hard question regarding that. And you all did pretty well in this. So we are going to extend the work on the Hooke's law by not only having a stress in one direction. In this class, we're going to have stress in multiple directions. And we're going to study the strain, like the strain due to all these stresses. Also, we're going to learn how to present stresses at a point. So if I told you, like the same rod that we've been using, and it seems like this rod is going to extend with us until the end of the semester, if we have this rod with the same force, and I told you, I used to tell you what is the internal force at B. It's like a pretty easy question for you. You can cut at B, like here, for example, this is the cut. And when we cut, we usually do this hatch thing. You probably know this from like engineering drawing. So whenever we cut, we make a hatch to indicate that we cut at this point. So the question that I used to ask you, what is the internal forces at B? So what would you do? You will cut at B, find the normal force, shear force, bending moment. Again, all these are forces. But the question that I'm asking you now, okay, what is the stresses at B? And not only you calculate them, I need you to not only calculate them, I need you to present them in a stress element. And this is one of the ways that we present stresses. And I think this is the only way, to be honest, I know. So let's go ahead and show you how we present stresses on stress elements. So first of all, if I told you, find me the internal force at B. From previous classes, you will cut at B, either work from the left side or the right side. Both of them are the same. And then now I chose to work from the left side, for example, and I still have 100 kips because I have a constant. There is no any change in force here. So all the cross section here gonna feel the 1,000. And we're gonna learn how to draw the normal force diagram in a couple lectures. But now I think you know that since there is no any change in any force here, so this whole cross section gonna feel this 1,000. If I added some sort of force here, which is 500, that's a different story. That's when we will divide the beam to elements, and each element gonna like resist different force. But now let's start with like simple 1,000 kips. So since there is no any change in normal force, so all these like throughout the beam length, it's gonna feel the 1,000 kips. So here at point B, so we have a normal force of 1,000 kips. Okay, how do we change the normal force to stress, given the area, the diameter here of 20 inches? So we basically, what we do to convert from force to stress, we divide it by area. So if we divided this force by area, which is sigma out of 1,000 over pi d squared over 4, I'm gonna get 3.14 KSI. What does that mean? That means every inch square in my cross section gonna feel the 3.14 kips. So if now I'm just like taking like a very further look. That's okay. So I'm just zooming in here now to this guy. You know that 3.14 is the stress. So if I draw a squares here of 1 by 1 inch square, each square here gonna feel the 3.14. Am I right? Because that's the stress. Every inch square gonna feel the 3.14. So now I told you, the question here asks you what was the stress at B. So B, for example, was somewhere here, for example. Here was B. So if I want to find the stress at B, at this point, what stress that this point going to feel? Anyone? The 3.14, right? Because it's going to be constant throughout the cross-section. Later in this, like next, I think lecture 10 or 11, we're gonna find that at certain points in the cross-section, the stress gonna change. But now, since we're still in lecture 3, let's say that any point in the cross-section gonna feel the same stress. So, just bear with me. If this is the square at point B, I know that this square gonna feel the 3.14. And I'm gonna take this guy out here. Okay? This is this face. Like, I can draw it hatched because you know that I cut here, which is like, okay? And I do have a stress here of 3.14. So let me ask you this. Was that normal stress or shear stress? Normal. So I'll put a sigma here. Okay? And if I want to extend this square inside the cross-section, I can extend it in a form of a cube. So I'm drawing a dotted line, and dotted line here means this is going inside the cross-section. Okay? And I'm taking, again, this cube out, which is an extension to this guy. Okay? And this is what we call a 3D stress element. But it's not complete yet, because if I have this cube that represents point B, and I have a stress going on from this side, I need to make this cube stable. So the stability here, it comes in form of summation fx and summation fy. If I took summation fx here, I'm going to find in the other side, which I'm going to draw as a dotted line here. And you understand by drawing this dotted line, you understand like this is the other face of the cube. I do have also another 3.14, which makes this cube stable. And in different words, I draw the square here, right? And when we cut, we found that the stress is 3.14. But this was due to our cut, which we cut this way, and we work with the left side. But if we cut from this way and work with the right side, and we will have the same square, we will also find a stress of 3.14 here. Do you agree with me on that? And actually, this is kind of logic, because every point in this cross section need to be stable. Because if I have 3.14 here and I have a 5 here, that means like this point is not stable. So you will find that this beam is moving to the left. And we don't see this in real life. We see like everything is stable, which means the force in the left is equal to the force in the right. Force in the up equal force in the down. That's why we have summation fx equals 0, summation fy equals 0, and we have summation moment. So this is what we call a 3D stress element. And since we have a general direction here, which is this is the x direction, this will be y, this will be z. So do you agree with me that I'm going to call this sigma x? Do you agree or no? Yes. Cool. So now, look at this. I want to convert this 3D element to 2D element. I just need a little bit imagination here. So I'm going to look, this is my eyes, and I'm going to look from here. What I will find is this square, and I will have a force that goes like this. 3.14, stress in x, 3.14. Do you agree with me? I'm looking at this face. So when I look at this face, I find these two are coming out. Okay? So was this tension or compression? Tension, right? So this is how we draw the stress element or that's how we represent sigma x in tension in 2D stress elements. So now this is 2D stress element, and this guy was 3D stress element. Okay? So I think now it's kind of obvious. If I want to draw the stress element in compression, if I have the southern kips, instead of being in tension, I have it in compression, so I will put it this way. 3.14, sigma x 3.14, KSI, and this is the negative, which is compression. This guy in tension. Do you agree with me? Okay. Let's now define another direction. So we now know how to draw the stress element, or how we represent the sigma x at a point in a beam in terms of stress element. So now I just took this beam that we saw before and I rotated it upside down, but I didn't rotate my axes. So I have x horizontal, I have y vertical, I have z like out of the page. So if I want to draw now the stress element at B, so let's do something like this, as if like I'm zooming in. Same force, same area, same everything. So where do you think I should put my stresses? In the x direction or in the y? Y. So the reason why we put it in the y direction, because if I now want to find the internal force at B, I will make a cut at B, and then I will find the 1,000 coming out of B. And that's what we're going to learn later, how we will find whether you're tension or compression. I'll put my hand on B, and what I find that the 1,000 is pulling my hand. So if it's pulling my hand, that means this section is in tension. So now it's in tension, but in which direction? In the y direction, right? So I will draw the stress element like this, but now it's sigma y 3.14 KSI, and this is how we draw the stress element in the y direction. And also, I don't need to mention that this is now positive because it's in tension, and if I want to draw it in compression, I would just make it, I'll just change the arrow that it's like pushing that 2D element. So this is a negative, this is a positive. Okay? So now you know how we draw the stress element in the x direction and in the y direction. Any questions so far? Yeah?
Yes, sir. I know it's positive and negative, but is that?
Tell me, which dot?
HE, or is that RE?
What do you mean?
Next to the tension and compression square?
This one, oh, it's VE, which is like, this one will be, so negative, so we take this VE and put it here. And this is positive, so we take the VE and put it here. My bad, I'm not explaining this. It's just like by default, I usually write that, okay? So positive and then negative, okay? So now let's like little bit define the stress element. So stress element is like a useful way to represent stress acting on a some point on a body. So where we can put all the stresses. So what we learned so far, we can put the stresses in x direction and we can put stresses in y direction. So let's talk about something else, which is one of the questions that you will find in exams, which if I give you some sort of a body like this and some sort of force, and then I'll draw to you how this thing gonna break. And if you know that this thing broke that way, what kind of stresses that cause this break? Is it normal stress or shear stress? Shear stress. So I will use my imagination in the exam. It's not gonna be hard. It's like it's gonna be. I have a question in my mind that's gonna be from real life. The only hint or the only thing that you need to know is how this thing broke, and from how it broke, you need to tell me if it broke in shear, where like a friction happened, or a tension or compression. So you all told me that this element broke in shear. So you agree with me, for example, if I make a cut at C, I have a shear force here of V, right? There is a shear force. And then lecture 11 or 12, we're gonna find how to how to calculate the shear stress in the plate. But again, shear stress will be tau. So imagine that I already find tau, okay? And I want to draw the stress element here, okay? So stress element either on the edge or any way inside the beam. So you know that if I would draw a cube like this, that I do have a stress that's going down, okay? So if I draw a cube here, I will have a stress that's going here, right? And if I want to, this is a 3D, and if I want to look in a 2D from this way, I will find that I do have a shear that's pointing this way, okay? We are still halfway through. We are not, this is not a 2D complete element, because if I want to make this, once you find one of the forces, or sorry, one of the stresses, you need to apply stability on that 2D element. So summation f, do I have summation fx now? I don't. Summation fy, so the other side gonna be looking up, same shear, same shear. So now I made this element stable in the y direction, right? So I'm sure that this element not gonna fall down due to this stress. I'm sure that I have another stress that keep it in place in terms of summation fy. But look at this. If I have this element and I'm pulling one side down and the other side up, what's happening here? It's rotating. So I need to counter something this. So if I want to counter this, I know that this element is now moving in the clockwise. So what I would do, I will add a similar shear, same stress up here, and summation fx now, I'll make it down here. Now, do you think it's stable or no? So it was first rotating that way. Now I put the same shear, same force, but in a different way. Now it's stable. So this is how we form it. So now let's talk about how we can quickly make it. So you need to make sure that the arrows meet either this way or, so the arrow meet the arrow and tail meets the tail. So heads, tails, tails. So let me draw it in a different way. If we had a shear in a different sign, so what would you notice? That I have arrow, arrow, then I also have an arrow, arrow here, okay? One of them is positive, one of them is negative. How do we find which one is positive and which one is negative? This is the sign convention for this. If you find that the arrow at the upper right corner, that means it's a positive. Anything else is gonna be the negative. So you wanna memorize this as if you have, if the arrow is meeting at the upper right, that means it's positive. So you have now as if you have this directly proportional. So whenever you have this directly proportional thing, you wanna memorize that it's positive. Just memorize the positive, and whenever anything is not positive, it's gonna be negative. Okay? So now I think that I completed the first objective of this class, and I want to test you in this right now. If I gave you an element, so now I think we know how to form the 2D element. And from now until I think lecture 12 or 13, I'm gonna give you the stress element, and starting from lecture 12, you're gonna form it. What we did now, we formed the 2D element. We started by the cut, and then we found the force, then we found the stress, and we put it in an element way. From now until lecture 12, I'm gonna give you the stress element, and then you're gonna work with this. Until lecture 12, you're gonna form the whole thing. So let me test you in this. If I gave you a stress element like this, and I told you This is 20 KSI, 20 KSI, 10, 10, and then I have a something like this, 50 KSI, 50 KSI. So I need you to tell me sigma x equal to what, sigma y equal to what, and the shear equal to what. So sigma x first. Anyone? What? Anyone? Yeah, just speak loud. 20 KSI? Do I get second on that? Anyone has like different opinion? That's right, it's 20 KSI. Because by default you will assume this is x, this is y, this is z. So in the x direction, I have a stress equal to 20 KSI. But is it positive or negative? Positive, because it's in tension. Okay, what about sigma y? Negative 10. What about tau? Negative 50. So it's not positive because the arrows doesn't meet at the upper right corner. Okay? That's why it's negative, and it's 50 because that's where the shear is. Is that clear how you can read the stress element? Okay? So let me show you something else. If I have a 3D element like this, okay. Now you already know that if I added a shear here, in this face, I will have another shear there, which is equal but like in opposite direction. And to make it stable, I'll put one up in that face, in the upper face, and in the bottom face, I'll put that one. Okay, now because we had a shear which was like up and down, we made it stable in terms of like rotation and summation x, summation y. What if I have a shear in that face, which is here? What if I have a shear here? So let me add or like initiate a shear which is this way. So again, this shear in that face. You tell me how I want to stable it. Let's start with the back face. How I'm going to draw the shear. Opposite to that, that's right. And now it's stable in terms of not moving right or left. But now it's going to rotate this way, right? How to counterbalance that? Again, if you can, what? So you know that it's now rotating this way. I don't know, it's not it's not something I can tell, but like this, it's rotating this way. But you will agree with me, if I want to counterbalance that, I want to add shear that's rotating the other way, right? So that I want to make it stable. And the general rule of thumb here is put the arrow where the arrow and the tail where the tail. And that's how you can make it stable. So now I have an element that's stable horizontally and vertically. Is that clear? Any questions? Okay. Let's do some naming here. So now I'm not doing, for the last couple minutes, I wasn't doing any mechanics of solids, just like showing you how we present it, the naming and everything. Any questions? Okay. Now if I have a cube like this, okay? Now I'm still also in the naming thing. I just like want to teach you how we name it so that we can do the mechanics of solid in the next slide. So I do have this cube, okay? And this cube, I have this axes, which is x, y, and z. This face and this face, they are both perpendicular to x. That's why we call them x face. Same thing with y, same thing with z. So y is top, And bottom, Z is this face, which is facing you guys, and the one in the back. Okay? Good? So now, if I want to draw all these stresses that might act on that block, I will have this guy here, which is axial stress, and it's obvious that this is going to be sigma x because it's in the x direction. And the one that goes the other way, I'm going to draw dotted because we don't see that, and now we see it, so it's solid, so it's also sigma x. So whatever comes from the faces in terms of sigma, they're going to have the face name or the direction name. So the y here going to be sigma y. At the bottom, dotted, 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 then solid, sigma y. The z is the same thing. Z, and then I have in the other way here, z. That was easy, right? Now let's discuss the shear, because the shear has like kind of, I don't want to say hard, but a challenging naming. So if I start the shear in the x face, so this face here, I have a shear. How I'm going to name this? So the shear here going to be named as, what face is this? You tell me? This x face. So I will start here with x. And what direction it's pointing? Y. So the shear naming here is tau xy. So the first one here for the face, and the second one is the direction axis. Okay? Now let's balance this force. If I want to balance that force, I'm going to go to the x face but from the other side and draw it pointing up. Let me draw it in green. So now this also going to be tau, which face? X face, which direction? Y. So it's tau xy. Now you tell me, I'm going to balance this shear from the y face, and I'm going to draw this guy here. You tell me, what should I name it? Yx, that's correct. And you probably know that I want to balance that one by adding 1 on the lower face. It's also going to be yx. What about on the z face? This one here. What do you think? Tau what? Tau z, then x. So I will put one on the other side here, which is tau z x. Is it clear? Yes. So now I'm sure that if you will go to the booklet here and you will read this, you know which face I'm facing, right or no? So if I have, so the one, don't look at your booklet, the one that I just like erased here. What do you think this face is? So if you know that tau xy, which is acting on that face that you don't see, so this one is what? Anyone agrees with him? Anyone disagrees with him? He's correct, that's a z face. Okay? All good? Can you now read the stresses? Yeah, tell me. What's your question? Yeah, sure. Let me do something cool. Moment. If I will take this guy. No. Okay. Topic 3. Yeah. There you go. Oh, no. Okay. 1 minute. Because I divided my screen here and then it wasn't divided there. Okay. Go ahead. So what were we facing? We were facing z. And we had tau xy, which was this way. We had also tau xy, which is the other face. We had tau yx, which is up and down. So that's why we concluded that we are facing the z face. Okay? And again, it depends on how you read the shear. So if it's tau xy, x is the face that is this acting on, and y is the direction where the tau is pointing. Okay? I have also another thing. Let me show it to you. If I draw a shear on this x face, you tell me the naming for this. So if I draw a shear this way, what face is facing? Like what face in that? That's correct. Yeah, that's correct. XZ. So you got it? Cool. Now let's do some mechanics of solids. And this is a 3D Hooke's law, and it's very important that you know how we conclude the equations. So, okay, this is a little bit hard, so I need you to focus now, and then you're gonna get it. So if I have a cube like this, and I do have stresses in x, y, and z, and all of them, they are in tension, okay? So my question to you is, what is the strain in the x direction? Before, when I asked you what is the strain in x direction, we only had the stress in x. So what would we do before if we have only one stress? Is we find a delta, which is FL over AE, and then we can convert the delta to strain. But that's only valid, the equation that we had, that was only valid when we have one stress. But now we have three stresses in different directions. So how can we find the strain in x due to all these stresses? So let me make it easy on you a little bit by telling you, okay, I have a strain in x. Which one, so this is the x direction, which one will cause elongation in x, which is like the axial stress here, that is directly related to strain in x? Sigma x, right? So if I want to find strain in x, the first term of the equation here gonna be stress in x over modulus of elasticity. How did I find that? If you remember before, stress is equal to E times strain, right? So strain is equal to stress over E. So the stress in x, so the strain in x, the strain in x due to stress in x, so it will be stress over E. Is that clear so far? And will stress, which sigma x over modulus of elasticity, will it cause elongating or shortening to sigma x? Elongating. That's why we'll keep it positive. Now, let's move to the effect of sigma y on a strain in x direction, okay? If I'm pulling a strain in y, what do you expect gonna happen in x? Is it gonna reduce or increase? Reduce. So I'll put a negative here. And strain in x relative to strain or like strain in y, isn't it a lateral strain compared to y? What was the definition of Poisson's ratio? So if we have a lateral strain, the lateral strain is going to be percentage of the longitudinal strain, right? Due to sigma y going to cause longitudinal strain to what? Strain epsilon x or epsilon y? Epsilon y. Because if I'm going to pull here, I'm going to elongate, and sigma y or epsilon y going to elongate, right? So strain in y here is the axial, and strain in x is the lateral. So if I want to find the lateral, so sigma x going to be a percentage, and the percentage we name it by Poisson's ratio, percentage times strain in y. Do you agree with me or no? X was lateral compared to stress in y. So if I wanna, instead of calling it a strain in y, I'm gonna use sigma y over E, which what I did is just I used this equation. So what I'm saying here is the strain in x gonna be portion, and this portion we named it last lecture with Poisson's ratio, gonna be a portion or a percentage of a strain in y, which is due to sigma y. Now tell me in the z direction, what is the effect of sigma z on the strain in x? So first of all, step by step, sigma z if I elongate it in the z direction, what's happening in the x direction? It's going to decrease, right? So do you agree with me when I put minus here, right? OK, now a strain in x, which is this way, is a percentage of the elongation that sigma z going to do. So what should I write here now? Sigma z over E. But what am I missing here? Is the strain in x going to be similar to strain in z due to sigma z, or is going to be a percentage? Percentage. Whenever there is a percentage, you're going to put your Poisson's ratio here. Now, you tell me, what is the strain in y? So always start with whatever going to be directly related to strain in y. So strain in y, what's going to cause elongation in y, or what's going to cause like direct strain to y? Sigma y. So what should I write first? Sigma y over E. And then start with looking at the effect of the other stresses on y. So let's start with x. So what should I write? So first of all, is it going to increase or decrease? Decrease. Put your negative here. And then? Ratio, so V, or Poisson's ratio, times what? Sigma x over E. So now that's the x portion. What about the z portion? What is the effect of strain in y direction when we apply stress in z? So is it going to increase or decrease first? So the effect of y on z. Sorry, effect of, oh my bad, z on y. So when I elongate in z, what's happening in y? It's decreasing, right? So you start putting negative here. And it's going to decrease by how much? So ratio times what? Sigma z over E. You also need to tell me the strain in z. You got it or no? OK, a strain in z. What should I start with first? Sigma z over E. And then what? Minus Poisson's time what? Sigma x over E.
Minus Poisson's sigma y over E.
OK, is that clear? Any questions? So it's important for me to show you how we derive this equation, because these equations are already given here in this table. OK? So you're gonna write it in your cheat sheet anyway, but it's important for me that you know where this equation came from. You already, all of you just derived them. And what we did here is just like they took the sigma x out and make this whole equation in terms of sigma x, which is like using math. But again, we are now in an era that we have calculator, so we can use any of this equation, and we can substitute this in our calculator with x, and we can make our calculator solve it for x. So we don't need to do the math to convert it to this lower table. Is that clear? And it's important to all of you guys that you know how to use your calculators, so that you'll not be able to do the math or calculus or anything. I'm not interested in seeing your calculus, because you already passed your calculus classes. So I just need you to use your calculator very well. Any questions so far? OK, let's start with this booklet example. If we have this element, and this element is 0.25 inch thick, so I will say 0.25 inch thick, and this plate has a plane stress of sigma x of positive 25.4 KSI, sigma y is 19.6 KSI. Find the strain in z direction, and find the delta t. Delta t or delta t or delta z. They all have the same symbol. And then it's telling you, assume that the moles of elasticity is 30 times 10 power 3, and Poisson's ratio is 0.3. So what the question asks us here is to find the strain in z direction first. So don't look at the table. I need you to conclude to me what is the strain in z, like what we did a couple minutes ago. What is the strain in z? Sigma z over what? Over E. Then, so when you derive the equation, assume everything in positive, although the question might have anything negative here. But if the stress is negative here, you will go here and put a negative here. Okay? But we are lucky that this question has everything in positive, which is same to how we derive the equation. But we derive the equation as everything in positive so that if any of the stresses that we derived was in negative, so you just put a negative in the equation, in that part, like negative in that part only. So the equation will still be valid. So continue. So we have strain in Z is equal to stress in Z over E, then minus what? Then and again, if you're having struggle, which I don't wish that you're having a struggle in deriving this equation, look at the table. But it's important to me that you understand how we derive those equations. So what do we have here? Do we have a strain? So do we have a stress in Z direction? No. So I will remove that part. It will be 0. What is the Poisson's ratio? 0.3. So I will say 0.3 negative. Or I will say 0, 0.3 times stress in X, which is 25.4, over 30 times 10 power 3 minus 0.3. Strain in Y was 19.6 over 30 times 10 power 3. What I was saying earlier, that if you have a stress X, instead of being positive, it was negative like this, you will go at this equation and you will just put a negative just in front of the sigma X. Okay? So I got strain in Z equal to negative 0.00045. And whenever you have a strain in a value and a sign, or whenever you get a strain, just like tell me a very short explanation here that it is in shortening. And you all understand why. Because from the equation it's negative, and because when we apply X and Y, it's reducing in Z. So you understand it from like the logic way and also from the equation way. But we're not complete yet. We are asked to calculate the delta in Z. So delta in Z is equal to epsilon L, because epsilon equal to delta L over L naught, or delta over L. So I do have a strain which is negative 0.0045 times the thickness, which is 0.25. And you understand like the conceptual meaning of strain. A strain is the amount of deformation per unit length, and we have a unit length here of inch. So if we know that each inch here gonna deform by 0.0045, and I do have an 0.25 inch, so every inch in 0.25 inch is going to be formed by this number, so that's why I multiplied them together. I get negative 0.001125. Now it has an unit inch, and I will say it's shortening. Is that clear? Any questions? I wish all of you watched the video, which is the like 20-minute video of the shear strain, because we're going to have an example of shear strain in an in-class assignment tomorrow. So if whoever didn't watch it, I wish you watch it, or after I explain this, if I have time, I can just go over it. So you all know that this is the stress-strain curve, right? So this can also be shear, like shear stress versus shear strain, which is, if you watch the video, you will know. But this is not my point. My point is, we all agreed that we have a plastic limit here, we have an elastic limit here, we have a yield stress here. And if I told you, how would you find the modulus of elasticity, which is from the stresses and strain, or the shear modulus from the shear and gamma equation, you will still have to do it from the linear region, which is plastic limit over, for example, strain at plastic limit. So the slope here gonna be your shear modulus or your elastic modulus. Sometimes, and this is what I'm gonna update in the assignment tonight, we are not interested in the history of what happened after the plastic limit. And sometimes, as I told you, the plastic limit, elastic limit, and yield happens so quickly that we can't track which is which. So, unless mentioned, so we can assume that the plastic limit equal to elastic limit equal to yield strength, unless I mentioned the otherwise. If I mentioned this thing, if I showed you this thing, plastic limit, elastic limit, yield, that's when everything is different. But if I showed you now this way, this is what we call elastic perfect plastic model of the stress strain curve. And what is this? We can write this. If I give you this as a yield, it is still valid to find the slope or find the modulus of elasticity from stress over strain, from this model, okay? Also, I had you last in-class assignment to tell me if you have a strain here, for example, of 0.02, for example, what is the permanent deformation at that strain? So what did you do? It was a very hard question that all of you solved very well. You go up here, and you would go down in a line parallel to the linear elastic line, and I had you eyeball this value, right? If we want to accurately calculate it, we can, when we go down in a line parallel to the linear elastic line, it means that both of them has the same slope, right or no? If both of them have the same slope, so you can simply, if you know this yield, you can say E is equal to yield over strain, and this strain gonna be this value, like this difference. So you can subtract 0.02 from the value that you got here, and it will take you to the accurate. So I had you to to eyeball it from a curve, and now you know how to accurately calculate it. Okay? This was also in the video, but I have to tell it because this is very important. If I gave you two stress strain curves like this, which one is ductile, which one is brittle? Again, ductile means the material that exhibit elongation before it breaks. Brittle material that exhibit little or no deformation before it breaks. So if you have something like this, which one is brittle, which one is ductile?
Red is brittle.
Which one?
Red.
Red is brittle? Anyone agrees with him? Okay, what about that one? Ductile. But if I showed you like an experimental like this, and I told you both of them had the same length before applying testing, which this is like the initial length for both of them, and one of them elongated this way, or one of them, like before it broke, it showed this behavior, and the other one showed that behavior. Which one is ductile, which one is brittle? Bottom is ductile. No, bottom is what? Oh, yeah. Yeah. Okay? Is that clear? Any questions? I want you, before coming tomorrow, to watch the shear strain part, which is only a couple minutes in the video. It's very important that because you'll be able to solve the second problem, which is I'm going to update tonight. Okay?